they internally connected. So all are working together to solve one particular problem. So that was from the point of view of improving the hardware and the processor itself from hardware point of view. In addition to that, now we have to improve the memories also, because the data and the instruction will reside in the memory, and for computational purpose, the CPU should be kept on feeding the data at a regular interval rate at the frequency where the CPU can work. And still, whatever the amount of memory, whatever the memory technologies are available, still from frequency point of view, there is a gap of 40% speed mismatch as compared to the processor and the memory at which it supplies the data to the CPU to do some kind of operations. Means almost 40% of the time your CPU remain idle because the data is not available with the CPU on which it will do the operations. So that gap has to be minimized drastically. Otherwise, just improving the microprocessor will not do the work because the data has to get supplied from the memory system. And nowadays, we are getting SRAM and DRAM altogether in the available in market, but SRAMs are better as compared to DDR-RAMs or DRAMs, SDRAMs. Why? Because SRAMs are made up of transistors and DDR-RAMs are made up of capacitors, because capacitors are cheaper. So huge amount of memory can be given at cheaper cost, but from performance point of view, SRAMs, static RAMs are better. And also consumes less power because transistor can hold the voltage level up to certain amount of time without refreshing. But if capacitors are used, then you have to keep on refreshing the power to retain the voltage level because they transmit the voltage to the environment very frequently. So we have to improve the technology for building the good quality of memory. At the same time, we have to increase the size of the memory where we can put lot many data, as we require huge amount of data to perform on this, and we want huge bandwidth so that large amount of data can be travel from one part to another at any instance of time. At the same time, we have to keep on reducing the latency of the memory so that whenever we give a request to the memory system, okay, give me this data, and the time at what it supplies me the data, this has to be minimized. That is what called latency. Another part of this was that we have to improve the bus system altogether. Bus system means through how different components are connected together through which the signal will transmit. So nowadays you are getting all the electronic devices like on single chip, system on chip. Why? Because the components are all together so closely tagged that the signal travel will take less time and also requires very minimal amount of power. The power consumption also keeps on reducing. In that way, in the same line, the on-chip interconnect has increased significantly, due to which we are able to speed up the systems of the computer. So after that bus system, I am not going to very deeper of technology. I just give you the idea that where the key issues are remaining and where we can do some kind of modifications. Now we have to apply parallelism in somewhere. Be it in hardware or be it in software, we'll see, but we are now concentrating on hardwares. After doing all this, because the transistors have been very small in size and lot many transistors at a huge scale are integrated in the processor, now we can build multiple logic circuits within the same circuit, and based on that, as lot many elements are there, can we do something like pipelining to improve the performances? So we'll apply pipelining in architectural level in instruction fetching. The same thing can be applied in case of any arithmetic operation also. There can be instruction pipelining, there can be arithmetic pipeline also. In a non-pipeline architecture, that was the case earlier. What used to be done, suppose that any instruction require 5 steps: instruction fetch, instruction decode, then suppose execute, okay, or opcode fetch, then execute, then store something. So for the time being, assume that 5 small stages are there in one instruction, and each such step takes t amount of time. Then to complete one instruction, it will require 5t. To complete another instruction, it will require additional 5t. So likewise, to complete 5 instruction, it will require 25t amount of time. Now in the pipeline architecture, if you follow downwards the image, what happens now? When one instruction is getting fetched, then the other sub part remains vacant. Now when the first instruction is getting decoded, by that time another instruction, because the fetching unit is now available free, second instruction is used to get fetched from the memory. The similar way, if we just keep on increasing the steps, we can achieve some kind of parallelism in pipeline fashion. Now to complete that 5 instruction, you see the first output of the instruction will come after 5t time, but henceforth after each t we will get one output available. So now to get 5 instruction to get complete, we require 5t plus 4t additionally, mean within 9t we will complete 5 instruction. In the earlier non-pipeline case, we require 25t amount of time. But designing the circuit and all has become much more complicated. But we can improve this way the pipeline architecture to utilize the hardware available to improve the performance of the system. So nowadays, at least 64 such steps are followed in case of modern processors, so that we can achieve much more number of pipelining, and we will make each stage very smaller. So that way, we can do multiple number of instructions getting executed, or the output of each instruction is coming after a very short interval of times. But the circuit design complexity remains your headache. Second, what we can do? We can overlap different operational units. Either we can have one control unit, under that lot many ALUs. ALUs means all the logic circuitry that will perform the job, and control unit will give the instruction what to do. So as you are having multiple such functional units like ALU with their memories, so at the same point of time, many instruction can be given to the multiple number of ALUs, and multiple such operation can execute in parallel. Similarly, there can be multiple functional unit of different logics. One will be for doing addition, another will be doing for dealing with the branch instruction, another maybe for floating point arithmetic operation, another maybe for integer kind of operations. So multiple such units are there. We can engage all of them in parallel to improve the performances. Obviously, with the cost of increase in the circuit design and additional cost of the circuits. Further, we can improve the speed by exploiting the data and temporal parallelism, like the case of array processing and vector processing. Multiple units of data can be given here. Further, to improve processor, what can we do now? Instead of issuing one instruction one by one, at the same point of time, we can issue multiple instruction to get execute if there is no dependency. Although that's not the case always, there are a lot many dependencies. But if those instructions which are independent to each other, we can issue to the CPU that two such instruction is given to the CPU to execute in parallel. And this kind of architectures are called superscalar architectures, where multiple instructions are getting executed at the same point of time. So pipeline is still there, but now instead of one instruction, you are given multiple sub instruction. For example, in the picture is given 2 such instructions is given on the same point of time. So that way we are improving with pipelining as well as multiple instruction at the same point of time. So this kind of architectures are called superscalar architecture processors. Further, what improvement is done? That instead of an individual instruction in one word, add multiple such instruction together and make a huge long instruction word. So multiple instructions are combined together. Now from the abstract level, it looks like only one instruction, but internally there are 4 or 5 instructions altogether. The CPU identifies all the different instructions. What advantage we get? Instead of going to the memory, take one instruction and give it to CPU, now we are taking at a time multiple number of instructions and giving it to CPU. So multiple times you don't have to come to memory for taking the instructions or data. So that way, we call this kind of architecture to be as VLIW architectures. So from single computer, we gradually move towards multi-core processors, from their multi-computer systems, from their clusters, grid computing. Cloud computing is separate part I am not going to discuss here, like the supercomputing, all this. So that way we have improved from the architectural point of view. But using multiple computers is expensive and requires additional effort, hardware and additional support from the hardwares also. So the designing of the hardware are very much complicated and it's expensive, so it cannot be given or offered to any desktop PCs within the budget that we have to purchase a laptop or desktop processors. So multi-core processors are, in compared to that, cheaper but slower. So what feasible solution for daily use can be done? That with all the laptops and desktop nowadays, graphics processing unit are coming as a unit. This is not supercomputers, but for traditional computers, we want to improve the performances for the commercial computers that you are having at your home or somewhere, the desktops. For processing the graphics, you have additional graphics unit that used to be called VGA card earlier. So what are these GPUs? These GPUs are nothing but like small CPUs, but having very low frequency, but at huge numbers. So now these are given for your image operation. Suppose you are playing games where it requires the each and every pixel to be simultaneously moved in a rotation or scale down or something. Then lot many operation has to be done at the same point of time. Otherwise, the movement of the elements like movies or something, it will not be so smooth. So with a cheaper cost, the GPUs are now given. Now you have the CPU plus you have the GPU. Can we use this GPU not only for the graphics operation but for our daily computational purpose? And this field is what called GPGPU, General Purpose Graphics Processing Unit, because it's available readily. You are not doing any game operation, but you have a graphics processing unit. Then can we use this GPU unit for our computational purpose, not for your gaming purpose or something like that, as these are readily available in your computer. So this field is called even GPU. So these are coming for desktop or laptops. So you can find there are n numbers of ALUs altogether. The control unit cache memory are like the same in case of GPU and CPU, that may vary in size. But the fundamental difference is there that you have n numbers of small ALUs where they have their own dedicated control unit and cache memory, and the DRAM is your shared, which is cheaper one. So you utilize this for our computational purpose to solve these problems. So the serial part, if you don't have a parallel processor, the serial part can be executed by the CPU, whereas the parallel part of your program can be given to GPU to work in a faster in parallel mode. That way we can utilize the GPU to do our basic operations. So this kind of GPUs are nowadays readily available in the market. You just purchase it, insert in your PCI slot, or externally you can connect so that you can improve your graphics processing operations.